Welcome to everyone. This is Analytic Number Theory, so hopefully you're all expecting this course here. So the first lecture today is supposed to just be an introductory lecture to give you a feeling for what some of the content in this course is going to cover. So rather than sort of starting the key content of the course, it's more of an overview lecture. And the course is called Analytic Number Theory, which gives you a good hint to what the overall aim of the course is. It's really a number theory course, so we want to prove results in number theory. Somehow to do with the arithmetic of integers in some way, but this is analytic number theory, so we want to use techniques from analysis and related areas. Using techniques. And I very much encourage you to try and keep this philosophy in your mind when you're going through the course and when maybe you're revising the course, that certainly some bits of the course at first sight might look as if they're doing lots and lots of analysis, estimating different functions and counting things, but I don't want you to lose sight at all that really this is a number theory course and not an analysis course, and the analysis is just a tool for the things that we're interested in the number theory. And so don't lose sight of the number theory, which is often where the kind of key ideas are, and the analysis is just a sort of technique or tool that enables us to get to the real number theory that's what's going on here. Okay, so that's a pretty vague overall aim, and so maybe a slightly more concrete key motivation question for the course is a question that's got a long history in mathematics, and certainly was a big question that Gauss asked himself, which in simple terms is, how many primes are there? So it might be that you've taken number theory courses before, you've read things, and you've maybe seen Euclid's proof that there's infinitely many prime numbers. And so maybe this therefore seems to be a slightly strange question, but I guess particularly from the point of view of this course, maybe there's an emphasis on how many, in some sort of quantitative sense, how many primes are there. And one way you can make sense of this, rather than just asking are there finitely many primes or infinitely many primes, is looking at the counting function of the primes. So maybe another question would be, how many primes are less than or equal to some number x for large values of x? We know that there's infinitely many primes, but how does the counter primes grow? And so to make this a little bit more precise, we can introduce the function pi of x, which I'm defining to be the number of primes which are just less than or equal to x. So this is a function of a real number x, and it just outputs the number of primes less than or equal to x. And so if you were to draw a graph of pi of x, it would be a strange sort of step function where it jumps by 1 whenever you get to a prime number. And so one way of trying to understand this question is saying, what is the size of pi of x and how does pi of x grow? And it's essentially unreasonable to expect a a very clean answer for precisely the exact value of pi of x. This is a genuinely complicated arithmetic function, and so there's not going to be any simple way of determining the precise value of pi over x. So the motivation and the point of view of this course is not to necessarily know exactly the size of pi over x, which is on the same order of complexity as understanding virtually all the primes up to x, but instead to try and get some partial understanding of the size of pi of x. And Gauss, as I said, asked himself this question, and he came up with a guess. And so Gauss guessed primes of size x occur with density roughly equal to 1 over log x. So he was just looking at tables and tables of primes, and if he was looking at many primes of size roughly 1 million, he thought that the density of those primes within all integers looked like roughly 1 over log 1 million. Similarly, if you're looking up at a billion and so on. And so one way to make this a little bit more precise would be to reinterpret Gauss's guess that the counter primes up to x should roughly look like the integral of this density 1 over log. So here I've written approximately equals. This is not supposed to have any precise mathematical meaning. It's just Gauss is saying that this complicated arithmetic function, pi of x, so we're thinking of this as complicated and interesting and very much arithmetic, should be well approximated by this simple smooth function. So this has no arithmetic in it at all. This is just a pure function from analysis. If you put in some huge value of x with maybe 20 digits or something, then your computer can tell you the value of this to whatever level of precision you want very, very quickly. If you put in some huge value of x here with 20 digits or so, it'll take your computer hours and hours and hours, and it probably won't ever get to the precise value of pi of x. So this is a complicated function, whereas this is a simple function that we feel we can understand everything that we want to understand about. Similarly, this is a nice differentiable function. You understand all its derivatives, whereas this is some much more complicated, messy step function. So Gauss was saying that this complicated, interesting object can be well approximated by this simple, easy object. But there's then this question as to what does approximately equal mean? And there's a few different ways you can interpret that. So one of, or maybe the main goal of the course is to prove the following theorem, which is known as the prime number theorem. There's various different formulations of this, but one formulation says that if I look at the difference between these two objects, then this is small. So this is less than or equal to some constant times x divided by log x to the power 100 for some fixed value of c bigger than 0 and all values of x at least 2. So I guess maybe it's worth mentioning that this function that I'm saying we can understand everything we want to about, this is of size roughly x divided by log of x when x is large. And so at least when x is large, so that log x is large compared to this constant c, that's saying the error in this approximation is smaller than either of these two terms. And so this is saying that pi of x is equal to the guess plus some error term, which is smaller by some large factor compared to the main term when x is large. But when x is small, this constant c might be some large constant, and so this really has no content at all. It's saying less than just maybe a totally trivial bound that pi of x is less than the number of integers up to x, which is x. So this really only has content when x is very large, but that's going to be very much one of the sort of mindsets that we adopt throughout the course, that we're really interested in these asymptotic estimates when some size parameter like x is tending to infinity. And it's only on these very large scales that these sort of approximations to interesting functions by smooth functions can become reasonably accurate. Okay, so this is one of the highlights of the course, and maybe the main aim of the course is to understand the develop a whole toolkit that allows us to study arithmetic questions like this and to prove results like this. But this isn't really what we believe to be the truth. So maybe I'll mention the conjecture, which is the Riemann hypothesis. So sometimes the Riemann hypothesis is called the most important open problem in mathematics. The Clay Maths Institute, which is based here at Oxford, gives a $1 million prize reward if you solve the Riemann hypothesis. And again, with the Riemann hypothesis, there's many different formulations, but one of them can be viewed as a improved quantification of Gauss's original guess. That the error between the difference between pi of x and this nice approximation is not just x divided by some power of log x, but x to the half times log x, again for some fixed constant c and all values of x bigger than or equal to 2. I guess in case you're still getting used to this formulation, the value of c really doesn't matter too much here. It's not supposed to be the same value of c, and we, because we're thinking of x as being very large, we really don't care what c is. We just want to know that there exists some constant c such that this sort of estimate works. Similarly, the value of 100 here is a number that I just chose arbitrarily. For any constant a instead of 100, you should have some constant here, but maybe that constant will depend on what you choose. So with a different constant, you'd have log x to 1000, and a different constant again, you'd have log x to 1 million, and so on. And when x is very large, log x is roughly the number of digits of x, so log x grows very slowly, and so x to 1/2 times log x is a lot smaller than x divided by log x to the power 100. This is roughly half the number of digits of x, whereas this has a very similar number of digits to x itself. And so this is really saying that these two things are very, very close to one another, whereas this is a weaker version of this. But the Riemann hypothesis is completely open. We don't have any idea of how to prove it, but we'll see through the course how the Riemann hypothesis fits into a more general scheme of these sorts of estimates. Okay, so those are introductory statements. So far I haven't proven anything or done any real mathematics, so maybe we should actually start doing something. And so I want to give a few sort of proofs about how you might get some weak estimates on things like counting primes by some easier arguments that are still based on ideas from analysis and combinatorics, which is the spirit of this course. So maybe we'll start off with a lemma, and these two difficult estimates are getting strong estimates on pi of x. We're going to today accept just some weaker estimates. So I want to get an upper bound of c times x over log x for some constant c bigger than 0 and all values of x bigger than or equal to 2. So if we remember from here, we're saying that our guess is of size, we're expecting pi of x to be of size roughly x divided by log x. And so this is rather weaker than this, but it's saying it can't be much larger than x over log x. We're getting the correct order of magnitude, but we're off by some constant factor c. So how might we prove this? Well, the key idea is to look at something that encodes the primes in a way that we can get a handle on. And we want to, in this context, look at the binomial coefficients 2n choose n. So this is 2n times 2n minus 1 up to n plus 1 over n times n minus 1 to 1. So every prime which is bigger than n and smaller than or equal to 2n appears in this numerator, but none of those primes divide the denominator. So every prime p which is bigger than n and less than or equal to 2n divides the numerator, but not the denominator. And so in particular, 2n choose n is a multiple of all of these primes. So we can write 2n choose n, and since it's a multiple of them and it's not 0, it must be bigger than the product over all primes p, which are bigger than n and less than or equal to 2n. But since every term in this product here, p, is bigger than n, this is certainly bigger than or equal to n to the power, the number of primes between n and 2n. On the other hand, this binomial coefficient appears as one term in the binomial expansion of 1 plus 1 to the power 2n, and all of those terms are non-negative, so it's certainly bounded above by this, which is 4 to the n. And so taking logs and rearranging, we see that the number of primes between n and 2n is bounded above by log 4 times n over log n. So this is very close to what we want, apart from we want the number of primes counted between 1 and x instead of the number of primes between n and 2n. But we can move between these pretty easily. The number of primes which are less than or equal to x is equal to the number of primes which are between x over 2 and x plus the number of primes which are between x over 4 and x over 2, so on. And for each of these, we can use our bound here log 4 times x over 2 over log x over 2 plus log 4 times x over 4 divided by log x over 4, and so on. And this series converges, and this is bounded above by some constant times x over log x. Essentially, when x is large, this is given a constant that's maybe just log 4. And so this is proven our result here. And maybe it's worth taking a step back and thinking, how did this work? Well, the whole thing worked by sort of this magical way of looking at the binomial factor. So the proof is somewhat unsatisfying that I took a rabbit out of a hat and then everything followed quite quickly from estimates on these binomial coefficients. But what made these binomial coefficients work was the key property was that 2n choose n had a multiplicative interpretation related to primes, and an additive interpretation which allowed us to get simple estimates for it. That if I just looked at the product of all primes between n and 2n, this is clearly related to the number of primes between n and 2n, but it's not obvious how I can get an upper bound for this quantity. And the key step here is this sort of additive relation that 2n choose n comes up from this binomial expansion. And this key property here of mixing addition and multiplication is something that comes up in lots of different places in the course. Primes are naturally multiplicative objects. They're defined through multiplication. And so anything that's getting a handle on primes needs to have some multiplicative structure to it. But if you want to count numbers of a certain size, this is fundamentally an additive restriction when you're putting size constraints on. And so you need to be able to somehow pass between multiplicative objects and additive objects. And here, the binomial coefficients worked because we had this product expansion and this sort of interpreting it combinatorially from this additive expansion. Okay. So that's one upper bound for the number of primes less than or equal to x. I'd now like to give a proof of a lower bound for the number of primes up to x. Again, mainly to motivate the sorts of ways that we want to think about things in this course. And so maybe I'll just state it in a simple way. There are infinitely many primes. And so as I mentioned, normally the textbook proof of this would be Euclid's argument for the infinitude of primes, but I want to give a slightly different argument which is originally due to Euler. And the spirit of the proof is going to be somewhat similar here. I'm going to, first of all, produce some slightly magic object that has both an additive interpretation and a multiplicative interpretation, and then deduce everything from looking at that. So consider the product over all primes less than or equal to some number j of 1 plus 1 over p plus up to 1 over p to the power j. So j I'm thinking of as some given fixed integer, and this is just some rational number that depends on j. We can expand this by just multiplying out all of these finite number of products and then grouping terms together. And so we can write it as a sum of numbers 1 over n for all n living in some set nj, where nj is equal to the set of integers in n such that if p divides n, then p must be less than or equal to j, because it must appear in this product, and p must divide n at most j times. So p to the j plus 1 does not divide n. So hopefully this is reasonably clear, but just to be totally explicit, if I had j equals 3, I'm looking at the product 1 plus 1 over 2 plus 1 over 2 squared plus 1 over 2 to the 3 times 1 over 1 plus 1 over 3 plus 1 over 3 squared plus 1 over 3 to 3. And this can be written as the sum of 1 over 2 to the a, 3 to the b, with a and b both being between 0 and 3, and that's precisely the set N3. So clearly, we have that 1, 2, 3, and so on up to j are certainly in the set nj. Any number which is less than or equal to j is certainly going to have all its prime factors less than or equal to j, and it's not going to be the j plus first, be a multiple of any j plus first power. So the sum of 1 over n for n in nj is bigger than or equal to the sum of 1 over n for n less than or equal to j. And then we can do maybe a simple integral comparison. This is certainly n up to n plus 1 dt over t, because 1 over t is always smaller than 1 over n for t between n and n plus 1, and the length of this integral is 1, and this is just equal to log of j plus 1. But on the other hand, so we have a lower bound for this product in terms of j, but on the other hand, this is a multiplicative object. And is naturally related to the primes going up to j. Well, these are the first few terms of a geometric series. All of them are non-negative, so I can certainly upper bound it by the whole geometric series. And the full geometric series is just 1 over 1 minus 1 over p. But every prime is at least 2, so 1 minus 1 over p to the power minus 1 is always less than equal to 2, so sorry, this is primes less than equal to j. So this is certainly bounded above by product over all primes less than equal to j of 2, which is just equal to 2 to the power pi of j. So this object here, we have an upper bound related to the counting function of the primes, and a lower bound just coming from our additive expansion. And so when we put these together, we find that pi of j is bigger than or equal to log j over maybe log j plus 1, but certainly log j divided by log 2. And this tends to infinity as j tends to infinity. And one nice automatic consequence of this Euler argument is that it's naturally quantitative, that not only are you proving that there's infinitely many primes, you're proving that there's at least a certain number of primes. So we know from the prime number theorem that the number of primes up to j is actually roughly equal to j over log j. And so this lower bound of log j is actually pretty bad. That's quite small, but it's an actually quantitative argument, and it has, again, this nice feature of this intermediate object that interpolates between addition and multiplication. And you can get size understanding on it from looking at it from an additive point of view, and you can relate it to prime numbers from looking at it from a multiplicative point of view. So again, maybe it's useful to take a step back and to think what's really going on here. I presented this proof just with finite products because maybe that's the easiest way to get the results. But the heart of the proof is related to what's known as Euler's identity, that the sum over n to the power s from n equals 1 to infinity is equal to the product of all primes p of 1 minus 1 over p to the power s all to the minus 1 for s bigger than 1. So and I wrote this relation here as sort of an infinite version, is closely related to this finite version. It's sort of an infinite version of this for the different values of j. And one thing to note is that this is not a totally trivial step, that I'm using the fundamental theorem of arithmetic that every integer has a unique prime factorization in being able to say this product is exactly equal to this sum when I'm expanding it out. So this is encoding and in some sense equivalent to the fundamental theorem of arithmetic. And the point here is that this multiplicative side is naturally related to primes, whereas this additive side is naturally related to sort of size estimates on the integers. And so this infinite identity holds for any real value of s bigger than 1, but as s approaches 1 and gets closer and closer to 1, this series looks more and more like the harmonic series, and so we know that that's getting bigger and bigger and bigger, and it's gradually tending to infinity, since every term here stays bounded. We saw that each of these terms in the product is at most 2. For the left-hand side to tend to infinity, the only way the right-hand side can tend to infinity is if there's infinitely many primes. So that's a different way of presenting essentially exactly the same argument here. But it so this left-hand side and right-hand side both depend on the number s, and in fact, as we'll see a bit later on, this is often called the Riemann zeta function. Which can be viewed as a function of s, and Riemann's sort of great insight was that you don't need to only consider this for real values of s, you can also consider it for complex values of s, and the complex values of s encode a huge amount of properties of prime numbers in terms of the Riemann zeta function, which can be understood because it has both this additive interpretation and this multiplicative interpretation. When you're looking at complex values of s, this can be interpreted as a meromorphic function on the entire complex plane, and you can use techniques from complex analysis to start getting good understanding of prime numbers in terms of properties of the Riemann zeta function. And so the Riemann hypothesis is normally not written as a result about Gauss's approximation for the number of primes. It's normally talked about as a statement about the non-trivial zeros of the Riemann zeta function. And the heart of the proof of the prime number theorem, which is one of the key things that we'll do in this course, is getting some weak estimates on the non-trivial zeros of the Riemann zeta function that are much weaker than what's claimed by the Riemann hypothesis, but is nevertheless sufficient to prove results about prime numbers. But the key intermediate step is this Riemann zeta function that's allowing us to encode properties about the primes in terms of this object that's then related to integers and therefore amenable to actually get a handle on and get estimates to, and is mixing up multiplication and addition. Okay, since we're doing reasonably well for time, I thought maybe I'd finish up by sketching one further lower bound for the counter primes, which is slightly better than what we have there, and it's also in the same spirit as this sort of estimate, which goes back to Chebyshev. The final lemma is that phi of x is bigger than or equal to some constant c times x divided by log x, so maybe I'll be slightly brief in the proof, but again we're going to look at the binomial coefficients. So a slightly more complicated estimate on the binomial coefficients, but is still not too complicated at all, is that 2n choose n is bounded below by 2 to the power 2n divided by 2n. So it's not quite the same size as 4 to the n, it's bounded below by 4 to the n divided by 2n. This is not hard to prove, but I won't do this now. Also, maybe I'll let VP of an integer m be the largest integer j such that p to the j divides m. And so in particular, this means that you can write the prime factorization of any integer m as the product over all primes of p to the vpm. But then we see that 2n choose n is equal to the product, well, over all primes, but the only primes that can possibly divide this are less than or equal to 2n of p to the vp of 2n choose n, but this is vp of 2n factorial minus 2 times vp of n factorial, just from the definition is 2n factorial divided by n factorial squared. And I can also split these up as products, and I can view this as a sum over all integers m of 2n over p to the m floor minus 2 times the sum of n over p to the m floor by just counting the number of terms in the product 2n factorial, which are a multiple of p, the number plus the number of terms which are a multiple of p squared, plus the number of terms which are a multiple of p cubed, and so on, is going to give me vp of n factorial, the number of primes that occur in total. And similarly for vp of n. Okay, but if it's not too difficult to see that so this floor notation means the biggest integer less than or equal to x. So the floor of 2x minus 2 times the floor of x is equal to 0 or 1, depending on whether the fractional part of x is smaller or bigger than 1/2. And so this means that this is certainly bounded above by product over all primes less than or equal to 2n of p times the number of m such that p to the m is less than or equal to 2n. And the number of such integers m is at most log 2n divided by log p. And this is just equal to 2n to the number of primes less than 2n. Okay, so now put in our upper bound related to primes together with our lower bound on binomial coefficients. This means that pi of 2n is bigger than or equal to maybe 2n times log 2 divided by log of 2n minus 1. And it's not too difficult to see that as soon as we have this, as soon as 2n is reasonably large, this 1 is negligible in compared to the size of this. And so you could certainly remove this 1 and put a factor of 2 in the bottom for example. And as soon as you have this inequality for any even integer n, you can similarly get the same inequality for any real number x. And so we get that pi of x is certainly big and equal to x maybe times log 2 over 2 log x for all x sufficiently large, maybe bigger than 100. And then this inequality is trivial by taking a suitably small constant for x smaller than 100. So again, this is fitting into the mentality that you can go through all of these estimates really caring about precisely what constant you have here in the log 2, but often this very much obscures what's really going on in the proofs, and the fundamental estimates that we really care about and end up being important tend to be these asymptotic estimates where we really just care about showing the existence of some constant c. And this means that we don't have to worry about small values of x. It makes things much simpler to think about. And maybe the first thing we'll do next time is to introduce some asymptotic notation that means we can go through arguments of this type without having to worry about small terms and explicit constants too carefully. And it means that we can streamline our arguments, making them focus on the key mathematical ideas rather than technicalities about the size of constants and things. But hopefully this has given you a flavour of the sort of things that we're going to encounter in the course. The key idea is that we're going to gradually build up the machinery that allows us to study primes and other arithmetic objects in terms of the Riemann zeta function and other generating functions that mix together additive behaviour and multiplicative behaviour. Okay, I think that's maybe enough for today, so maybe I'll pause here. Please ask any questions. Well, please interrupt and ask any questions at any point, but in particular, are there any questions now at the end of this first lecture? Okay, great. Seeing no questions, let's leave things here, and I'll see you all tomorrow at the same time.